So I mentioned that I had wanted to talk about parsers for a little bit. So that's what this video is going to be about. Is we'll just spend 20 minutes sort of give you an overview, because to go into any real depth with this is going to take a few weeks of material. It's really meant for a compiler's course more than a programming language course. We want to focus on the second side, right? After we've built up the abstract syntax tree, which is the sort of computer readable form of your code, how do we turn that into computation as opposed to how do we turn your human readable code into the AST? And that's what the parser does, is it takes my human readable code that you just typed up in your editor and turns it into a bunch of nested statements that the computer can eat. Right, so if we just talk about arithmetic, right, we might want to take something like this, 1 plus 3 times 2, and convert this into plus of const 1 mult of const 3 const 2. Right, and you can see the translation might not be too hard, but what happens is there's a lot of ambiguity in the way that we write stuff. I mean, you might have even seen a few memes about this, which is, how do we know that this is equal to 7, right? I mean, that's the natural way that we'd go about it. We see 3 times 2 is 6 plus 1. And the only reason we do it this way is because we've all been trained to do it through our elementary school days, right? We learned PEMDAS, the order of operations, which tell us which of these things gets precedence, right? Precedence. Because otherwise, it's totally natural to sort of say, well, 1 plus 3 is 4 times 2 is 8. So this should be 8, right? And depending on how well you remember PEMDAS, that might be a basic confusing fact. But this is actually 7. So we want to know, how can we make sure that whenever a parser sees a statement like this, it gets converted into this line and not this one, right? Mult of plus of mult const 1, const 3, 2. Right, assume the consts are in there. Right, we definitely don't want this one, but we do want that one. And it turns out this ambiguity, right, happens mostly because of this infix notation, right? That's the idea that between the two things we're adding, we put the plus. There's another form of notation called Lisp notation, or reverse Polish notation. The Poles are excellent mathematicians, and they did a lot of work on early logic and stuff. So they were the ones who first came up with this form of prefix notation, which resolves all the ambiguities of at least arithmetic. So this is where, instead of putting the operation in between things, which causes this kind of ambiguity, we put the operation at the front, right? So we translate this into plus 1 comma multiple of 3, 2. And if you notice, this looks almost identical to this, except that we've replaced plus with the plus symbol and multiplication with the multiplication symbol. And that's actually why the ASTs work so well, is because they're essentially in this reverse Polish notation already. It's a fairly easy thing that if we wrote all of our code like this, we would naturally be able to sort of, the parser step would be much simpler. And in fact, Lisp is a programming language that does all of its computations like this. So when you see Lisp, you see a ton of parentheses like this. Modern form of Lisp is Clojure, which runs on the JVM. So it's interoperable with Java and Scala as well. But yeah, this is a little bit of an aside. Basically what we want to do is always turn anything that's sort of ambiguous and follow some proper grammar rules to turn it into something that is unambiguous like this. And of course, if you think about an actual programming language, we're not dealing with just the ambiguities of adding and multiplying, but we're dealing with things like declarations, and like maybe even in the C world, we might have something like this, right? Where we're assigning X, Y, and Z to all be 10. and we do this weird chain of things. So really, where do we start, right? Do we start on the left-hand side, at which point y is not defined yet, or do we have to start, like, where do we put our parentheses in for this to actually make sense? And that's what parsing is all about. So yeah, let's talk a little bit about how you would actually, a parser would actually go about taking something like this and turn it into something like this. And what it does is we have another context-free grammar. A lot like the inductive definitions that we were talking about before. In fact, the grammar is essentially the same structure, but as I mentioned, there was the synthesis or the analysis direction and then the synthesis direction. In the inductive grammar stuff, we were all doing analysis where we started at the top and we had an expression already. We had one of these things, and we want to know, how do I break it apart into its subcomponents, and then do stuff on the subcomponents and build it back up. Over here, what we want to do is we want to do the, because we are building a abstract syntax tree, we want to go in the other direction. We want to do the synthesis, which starts with the lowest aspects, or the smallest aspects of this statement, and builds it up into the full thing here. So we have something that looks like this. We have like an expression. This could be something like a term plus an expression, or it could also be something like a term minus an expression. We could have a term that will turn into, it could be like a singleton times a term. Another term could be something like a single thing divided by a term. And then a single will be, say, a string, or it could be an int or something fundamental down here, right? Some sort of, maybe a char. So the idea is that and a term could also just be a singleton. So the idea here is that we have sort of our fundamental component parts, the singles. They can be combined into terms, which can then be combined into expressions. And this is done in such a way that we naturally obey our grammar rules, right? So the way that we might break this down is to try to sit down and be like, okay, so what singletons do I see? I see a 1, I see a 3, and I see a 2. Those are all singletons, right? So this is a single, this is a single, this is a single. They combine together, or this one, right, is also a term. I see that this is a singleton times a term, so I can use this to turn it into a term as well. And then this is a term, and then I see a plus between two terms, and maybe a term can also, an expression could also be just a term. The goal of having these sort of separated out as a singleton term or expression is to give the precedence structure properly. And so we end up with a term plus a term, which is then an expression. All right, so we have the const 1 and then the mults on the inside. It gets a lot more complicated than that, right? This is just for like a very basic little structure, but you can kind of see that what a parser, the way a parser really works is from this bottom-up perspective, sort of taking the smallest chunks, figuring out which of those can be combined into larger chunks, and larger chunks still until we get to a single sentence like this, which then our interpreter will go down, top down, and figure out what exactly does this mean, right? But yeah, to go into any more depth, there's a Jupyter notebook you can browse through that goes through a little bit more than this. But otherwise, it won't really be covered in this course, but it's useful to know because nonetheless, it's a part of programming languages that you can't avoid. But yeah, key takeaway, this just takes our human readable code, turns it into an AST, which our interpreter can then turn into computation.